on advanced encryption. And we will start with the first talk, which is about resolving the efficiency utility dilemma of threshold linearly homomorphic encryption via message space adapter. The floor is yours.
Yeah, thanks for your introduction. Hi, I'm Yijia. So this is a joint work with professors Rongmao Chen, Chao Lin, Songze Li, and Xinyi Huang. So this work is about threshold linearly HE. So just like linearly HE, threshold linearly HE also supports to perform linear functions over ciphertexts. Specifically, if we have the ciphertexts of M1 and M2 and two scalars alpha1 and alpha2, we can obtain a valid ciphertext of alpha1 times M1 plus alpha2 times M2. So in addition, threshold linearly HE also supports to distribute the secret key among N parties so that at least the T participants can decrypt. So specifically, each decryptor will compute a decryption share from its secret key share and the ciphertext. And hopefully, by combining those decryption shares, we can obtain the final result. By these two features, threshold linearly HE have a large number of applications. In particular, we started this topic because we believe it is a good building block for multi-party FHE. So for sure, every application will have so many options as a building blocks. Still, we believe the threshold LHE will have a special advantage for low communication cost. It has a pretty simple workflow to just encryption, evaluation, and threshold decryption. It does not require frequent party-to-party interactions, so the communication complexity can be pretty low, and it will have advantage if the number of parties are pretty large. However, when we truly use threshold linear HE to construct some large-scale applications, like federated learning with thousands of parties and blockchain with million parties, it is not as efficient as we expected. The reason is that its computation complexity is pretty high for the threshold decryption. So the total running time will still grow very fast with the number of parties and make the efficiency less impractical. Luckily, we still have 3 schemes with quasi-linear complexity. However, these schemes all suffer from utility restrictions. So for DDH-based exponential LGML, it requires to solve a discrete logarithm. And this step is practical only if the message is from a small known set. However, in practical applications, we usually have a large message set. And for those lattice-based threshold fully HE, so successful decryption, they assume that there exists a predetermined set of decryptors. So for example, the party 1 and the party 3 can successfully decrypt, but not for other decryption set. This does not hold in practice because in practice, the parties may not be online due to loss of interests, random dropout, or even denial of service attacks. In the past more than 20 years, although we have explored various threshold LHE schemes, we still suffer from this efficiency utility dilemma. So we would like to ask why threshold linear HE has this long-standing dilemma and how can we resolve it? Here is a quick answer. We all know that the security of these schemes are based on some hardness assumptions. For example, DDH problem, factoring-based problem, and lattice-based problems. And these problems will give the encryption scheme some features, like the small message space, unknown group order, and noisy recovery. And these features will make the HE either restricted or very challenging to be thresholdized. So as for the hard thresholdization, you can imagine that the well-known Shamir secret sharing does not apply. So existing works has tried to solve this problem by devising a stronger hammer, a stronger secret sharing, and that does not help to resolve this dilemma. So our perspective is maybe we need to try those easy nails. So we established the first LHE with easy thresholdization and flexible utility. Now here are some technical details. We need to imply the secret sharing technique. It has 2 algorithms, share and reconstruct. If we have enough shares of the secret S, hopefully we can recover exactly the share S. And Shamir secret sharing works as follows. It is basically the linear combination of shares, and the coefficients are so-called Lagrange coefficients. It is in this form, and if we need to compute the Lagrange coefficients, we need to know the group order P. So it must be a public information. And Shamir SS is pretty efficient because we can reduce the complexity to n log n with a number theoretical transform. So for factoring-based threshold LHE, it assumes that it's hard to compute P and Q from their product. However, the group order in this case is the Euler function of n, which is equal to P minus 1 times Q minus 1. So if P is a public information, the P and Q will be disclosed. So in these schemes, we need to keep the P and keep the group order as a secret information to avoid the leakage of P and Q. To solve this problem, the typical solution is called clearing out denominator technique. We just multiply a large number that is a factorial of n with the original Lagrange coefficients. So the new coefficient L prime will become an integer without a mod p. However, in this case, the new coefficient will be super large, and when we aggregating those decryption shares, we need to compute this exponentiation. So this will make the computation less efficient. For DDH-based schemes, we have CL framework who have already tried to improve the small message space restriction by modifying the internal mechanism. However, this still results in the unknown group order problem, and it's still hard to be thresholdized. So our mentality for constructing those easy nails is maybe we can improve exponential LGML, that is both flexible message space and easy to be thresholdized. So our key idea is to equip exponential LGML with an external adapter that doesn't modify its internal mechanism. So suppose that we have the exponential LGML message space is M down, and we need to construct the message space adapter method from M down to M up. Then we can return and improve the exponential LGML with message space M up. However, such a tool does not exist at present, so we formulate one. It has 4 algorithms. For encryption, its message space should be M up, and its secret key encryption and its key space should be M down. And we also require it is homomorphic in both of messages and keys, so that we can compute the ciphertext of FM on the FEK from the ciphertext of M with KEK. So with this method, we can construct the required HE. For example, we have 2 messages, M1, M2 from M up. We just use the method to handle the messages and use the original HE to handle the key, because the key space is exactly the message space of original HE. And so that's the evaluation step by the homomorphic, because it is homomorphic in both of keys and messages. Now we can successfully decrypt M1 plus M2 from the ciphertext. So HE up is obtained by simply combining HE down and method together. So another perspective to thinking about a method is hybrid crypto system. So in hybrid crypto system, we usually combine the convenient, concretely efficiency of secret key encryption and easy key generation of public key encryption. And our method is basically use a flexible message space of method and the easy to be thresholdized feature of exponential LGML. So since we do not modify the key pair, the key generation algorithm and the decryption algorithm, so any method for thresholdizing original HE can be directly used to thresholdize the new HE. It's just like this way. So now the only problem left is how can we build a lattice-based, how can we build a method for exponential LGML? We believe lattice-based encryption is a good fit. It satisfies all the requirements. Its message space is flexible, And its key space consists of small entries like -1, 1, and 0. In addition, it's homomorphic in both of messages and keys, so everything looks fine. However, here's a problem. The key and error in the ciphertext will grow very rapidly with a multiplicative factor big O alpha. So decryption will fail if the key or error exceeds some bound. So we use a bit decomposition idea. So we do this to alpha and suppose that we have multiple versions of m, that is m, 2 times m, 2 to the 2 times m, etc. So we can compute alpha times m as a linear combination of those multiple versions of m. And this will help to reduce the growth from big O alpha to big O log alpha. This is a final result. This is a final practical effect. So exponential LGML cannot handle 64-bit messages, but with the help of our lattice-based method, we can, and we can even evaluate a large number of messages for these functions. So we have all building blocks, and just combining them together, we obtain the threshold lattice exponential LGML. We analyze its complexity. It is the first unrestricted threshold LHE with quasi-linear computation complexity and constant communication complexity. So we also implement a prototype to validate the theoretical analysis. So in addition, if we take the message size M and the method case size D into consideration, our scheme will have even more advantages for larger messages. So it's basically linear complexity. And the third part we will discuss is how to thresholdizing lattice-based threshold FHE. So for lattice-based schemes, we cannot directly compute the inner product of ciphertext and the secret key because it will leak the error term in the ciphertext. And so a general idea is to add a large flooding noise term to the decryption result so that the flooding noise cannot be too large to break the correctness. However, it should be sufficiently random to hide the error term. So our previous work showed that the core of multi-party FHE design is to construct a new primitive called approximate secret sharing. It basically recovers an approximation B prime from the shares of B. So the difference between B prime and B should be random but small. And all of these existing works on multi-party FHE follows the same idea called noisy share. And we argue that encrypted share could be a better idea. So here is how to construct an approximate secret sharing via threshold lattice exponential LGML. So to share a secret B, we just encrypt the B using our scheme. And the share of party I consists of SKI, PK, and the ciphertext of B under PK. To recover the approximate secret B prime, we asked each party to encrypt local noise Ni and summing all ciphertexts up. And now we just need to use a threshold decryption to decrypt the final message, which is equal to B plus the summation of Ni, which is an approximation of B. And it seems that we can also resolve the multi-parties FHE's efficiency and utility dilemma. That is, our scheme can work for any T decryptors, and the complexity is pretty low. Or however, it's at the cost of an extra communication round. So for summary, all of the existing threshold LHE schemes are considering how to devise a special secret sharing for thresholdizing LHE, and we consider that maybe we should devise LHE that is friendly to existing secret sharing. And we propose method which seems a valid way to work well, and we believe method could be of interest, independent interest with more applications. Yeah, that's all. Thank you.
Any questions?
Thanks, this is really cool. I'm not sure I understood everything in detail, but in one of the last slides, you had decryption, which included noise contributed by the parties.
So you mean this part, right?
Yeah.
Okay. So the noise of the size of the noise is dependent on the security parameter, right? So in general, it has a exponential order with respect to the security parameter. However, recent works have considered the polynomial order. But no matter which order, so our focus is how to combine this noise with final decryption. So the distribution say, so we do not very care about that.
Okay. Yeah, I was just a little concerned, and the question is it brittle? Is it, you have to be very careful about where that noise comes from and who provides the noise last. If you have like 5 parties decrypting, 4 of them are dishonest, 1 of them is honest, and they provide their noise after the first one. Are there ways of biasing this at all, or do you have to, does the encryption take care of that?
So you mean we should consider the malicious version of it?
Yeah.
Oh yeah, sure. For sure, this paper considers only semi-honest adversary, and to extend it to malicious adversary, we discuss it in the full version of our paper, and we believe there exist enough tools for us to for such a malicious adversary. Yeah, so we believe some people will do this work later, but this paper we do not consider this adversary.
Great, thanks.
Yes, thank you very much.
Any other questions? All right, let's thank the speaker again. Okay, our next talk will be on general functional bootstrapping using CKKS.
Hi all, my name is Andrea Alexandru, and this work is with Andrei Kim and Yuri Polyakov. So let me start with the background on FAG schemes and the research question that we're posing in this work. So it's very common in FAG history to talk about generations of scheme, and I'm going to do just that, but with a twist. So the first actually fully homomorphic encryption scheme was proposed by Gentry in his PhD thesis, and there were many key ingredients in it, starting from using ideal lattices, introducing bootstrapping, circuit squashing, and so on. And then the Van Dyck scheme was also building on this blueprint, but used approximate integer GCD. So I would call this first generation as the unicellular life appearance in the FAG world. So while, full of breakthroughs, it's currently not considered practical to be used in current computations. So we move forward in time and we go to the second generation, which is described by a wave of works which introduced schemes using learning with errors and its ring variant. And the currently most used such schemes are the BGV and BFV schemes. And quite a lot of extensions and optimizations were introduced, especially the CIMD packing, which made the leveled version of these schemes very practical, but still bootstrapping is considered a bit slow, although I want to mention that there are very exciting works changing the state of the art here. Moving forward to the third generation, the GSW scheme introduced asymmetric noise growth for multiplication and sort of was the starting of a new generation of scheme, specifically hybrid schemes, starting with the Dukas and Michiancio paper, which proposed a hybrid crypto system between LWE and GSW, and also introduced the idea of functional bootstrapping, which is of interest in our paper, which is the capability of bootstrapping a message, but also applying a function in the form of a lookup table at the same time. And then the TFHE scheme by Kiroti et al. Introduced many optimizations and reduced the this functional bootstrapping time to under 0.1 seconds. And while a very versatile generation, the main efficiency limitation is that bootstrapping can only apply on a scalar message at a time. Moving even further, in our fourth generation, we have the approximate homomorphic scheme. And this is the CKKS scheme, which also introduced very novel ideas of actually combining the error with the message. So the error can corrupt the least significant bits of the message. But this introduced quite a lot of efficient implementations, for example, rescaling of encrypted messages and efficient polynomial interpolation. And this works very well with a fixed point representation of real and complex numbers. So while this scheme has the best bootstrapping throughput out of all the generations, it does not currently support functional bootstrapping, especially for arbitrary functions. Right, so our research question and what we want to solve is to actually get the best things from all the generations. And in particular, we would like to have a fully homomorphic encryption scheme that has very good throughput, but also is very general in terms of functionality, so can achieve this arbitrary lookup table evaluation at the same time. Okay, so our answer is positive, and we construct such a scheme. In particular, we construct a vectorized hybrid crypto system that has this arbitrary functional bootstrapping capability. And in more detail, in spirit, you can think of our scheme as a vectorized version of the DM blueprint, where we replace the additive LWE scheme with a vectorized scheme, its ring version. And this is also, you can think about it as BFV in coefficient encoding, which is also an additive scheme. And then we replace the ring GSW by CKKS. And in CKKS, we devise a method for constructing a functional bootstrapping capability. So we show how to evaluate arbitrary lookup tables while controlling the noise of the message. And the main tool we're using for this is trigonometric Hermite interpolation. And then, so we start in this additive BFV, we go back to the additive BFV, which makes our hybrid scheme an exact scheme, which is of interest, with the INCPAD attacks. Okay, so there is actually a wave of works proposing such hybrid crypto systems that do vectorized functional bootstrapping. So I think they deserve their own generation. And to continue with this cryptobiology analogy that I made, we're probably going to have AI integrated in biological systems. So, a new kingdom will arise. So I use this analogy. And in this new generation, I want to mention the work of Liu and Wang, who did vectorized functional bootstrapping using BFV. The works of Bai et al., who proposed initially functional bootstrapping for Boolean CKKS, and then in concurrent work, they extended to small plain texts. And there was quite a lot of works that inspired this new wave of schemes, starting from the Chimera paper of Bura et al., continuing with the Breach paper by Drucker et al., and the Chung et al. Paper, who discussed about evaluating LUTs, but using a complex exponential encoding of CKKS. Okay, so let me discuss more about the tools that we're using. And I will start actually with describing CKKS bootstrapping. So in CKKS bootstrapping, we're not actually evaluating the decryption algorithm under encryption. But what we're doing is that we're first extending the ciphertext to a larger modulus to be able to perform more computations. But this also introduces a number of integer overflows, which we then have to remove from the message. And in practice, this is commonly done by a scaled sign approximation, which is only accurate as long as the message is much smaller than the ciphertext modulus. And while this does the job and recovers the plain text, it doesn't do more than that, right? So we want to see how to expand CKKS bootstrapping to also be able to enable general lookup table evaluations. And as a hint of what's to come, actually this scaled sign approximation can be interpreted as a one-point trigonometric Hermite interpolation, where that one point is 0. And we are setting a constraint over the function at 0, and also a linear constraint over the derivative of the function at 0. Okay, so let's move on. If we want to approximate, to evaluate a lookup table for a message in ZP, we can look at p-point trigonometric interpolation. And we need the trigonometric part because we have to be able to remove those periodic overflows. So this takes care of that. And we can set at the p points of interest, we can set our interpolation polynomial to take the values of the function we want to evaluate. So this is good. This would be a good solution, but we would be evaluating this polynomial in CKKS, and we call that CKKS is a noisy scheme which introduces errors in the message. So because we want to have an exact message and go back to BFV, we actually need to make sure that the message is not corrupted by any errors, and just doing the trigonometric interpolation might actually introduce errors in the results. So we need a method to reduce the noise, which is why we look at initially at first order trigonometric Hermite interpolation, which apart from the constraints that I mentioned before, also sets constraints on the first derivative. So this smoothens the function. And this was also observed for the Boolean case in the bootstrapping bits with CKKS. And so this is a function that involves both cosine and sine. The coefficients are not integer. So we wrote it in a more convenient form and easy to generalize using actually the complex exponential function. And then we can evaluate the power series for this complex exponential function, which have really nice properties that the magnitude is bounded by 1. So you're not getting overflows. Then we evaluate a complex polynomial over it, which is of degree p-1, and then extract the real part. And this p-1 degree polynomial we're evaluating using the Patterson-Stockmaier method, which requires roughly square root of 2p homomorphic multiplications. But why stop at the first order? So what if we want to do more noise cleaning? And we also derived convenient analytical expressions for the second and third order trigonometric Hermite interpolation, which means that we're setting also the second derivative to 0 and maybe also the third one to 0. And to illustrate what this does is that the higher the order, the wider the plateau at the point of interest is going to be. So you're reducing more noise from the input. Of course, by setting more constraints, you're also increasing the degree of the polynomial you're evaluating, which means that in CKKS, you're introducing more noise. So it's a very interesting trade-off between the noise reduction you're getting by going to a higher order and the noise that you're introducing by evaluating this polynomial. Okay, so now I'm going to put everything together. The scheme we're proposing is this hybrid between RLEE or additive coefficient BFV and CKKS. And so for a message, a vector of scalar messages in ZP, this is how the RLEE ciphertext looks like. And then we can also interpret this as a CKKS encryption in the coefficient encoding of a message scaled by P, the plaintext modulus in RLEE, and with a scaling factor of Q, the ciphertext modulus in RLEE. But as I mentioned before, so the noise is included with a message here. So of course, we have to have a way of controlling this noise and making sure that it doesn't overflow when we're doing decryption. And I also want to mention that switching between these two schemes is actually cheap. It only involves modular switching and scaling. But however, there is a bit of a noise because we're switching from power of 2 moduli to entity-friendly moduli. Okay, so just the highlights of the algorithms. We proposed a method for evaluating arbitrary lookup tables on encrypted vectors of integers. And we're doing this by switching to CKKS. But I want to mention that the lookup tables we're supporting can actually have different input and output sizes, which is common in the DM-CGGI world. We try to follow the same workflow of CKKS bootstrapping. And there's not an issue, the fact that we're working with additive BFV as input and output scheme, because if we want to do leveled computations, such as multiplications and rotations, we can do them while in slot CKKS. And finally, a pure CKKS functional bootstrapping is also possible. Okay, so to describe a bit our evaluation, first of all, we released this in OpenFHE as open source implementation. Feel free to play with it. What I want to highlight here is that if we fix native integer size of 64 bits, which limits the CKKS scaling factor, we managed to implement arbitrary lookup tables up to 14 bits of inputs. And so single-threaded results under 9 bits, for LUTs with inputs of under 9 bits, we actually get less than 1 millisecond per slot. Okay, but what about going to higher precision? Because 14 bits is not that much. So very briefly, we also introduced a homomorphic digit decomposition algorithm following the blueprint of Liu et al., but we're using a single bootstrapping instead of two. That blueprint was for the CGGI scheme. And using those digits, we can then use chain and tree-based methods to evaluate larger LUTs by using only smaller LUTs. And our method also supports multi-value bootstrapping, where essentially if you want to evaluate multiple distinct LUTs over the same ciphertext, we can do it more efficiently than independently evaluating each LUT over the ciphertext. So the bottom line is that our method, using CKKS as a black box, can achieve the same multi-precision techniques as in the DM-CGGI world. And again, briefly, I just want to mention that, for the sign evaluation, which is a simple and nice function that can be chained, we managed to achieve also evaluation over 32 bits of inputs, 32-bit inputs. And there's also the interesting trade-off of how are you selecting your digits. So we want to work with smaller digits because this means smaller complexity of the functional bootstrapping, but also we want to work with few digits because this means fewer functional bootstrapping algorithms. Okay, so I'm going to now briefly compare with other methods and then conclude. So for more detailed comparison, please see the ePrint. Here I'm just focusing on a very common use case and that's seen in practice. So for example, the 8-bit LUT evaluation, you can find it as an S-box in the AES evaluation. We saw in the PBML workshop that LLMs are being quantized to 8 bits and so on. So for this particular size, compared to the vectorized methods, so the Liu and Wang method and the Bai and al. Method using BFV and CKKS, we are 5 and 9 times higher in throughput. And then compared to the CGGI-based methods, either using functional bootstrapping or circuit bootstrapping, we are several orders of magnitude better in throughput. Now for the sign evaluation using the multi-precision method, compared to the same blueprint that used CGGI, we are also 3 orders of magnitude higher in throughput. And compared to the multi-precision PBS implementation, again, using CGGI or DFHE, we're also 20-50 times higher in throughput. But throughput is the important word here. So I'm talking about amortized latency. If you care about total latency, you need at least several hundreds or several thousands of slots to work with for our method to be more efficient. Okay, so to conclude, in this new generation of FHE schemes, we proposed a hybrid scheme, which is capable of evaluating arbitrary lookup tables over vectors using CKKS. And this functional bootstrapping method that we're introducing also has the capability of error reduction. And then we can also expand it to multi-precision versions. But this is just the tip of the iceberg. And I think it's a very exciting era in FHE research right now with several new questions. So first of all, how do we extend to larger arbitrary LUTs, so with higher precisions? And we have some preliminary results on that with collaborators from Paris-Saclay. But so it's one thing to want arbitrary LUTs. If you want arithmetic operations on very large inputs, the next talk is going to be the solution for you. Then moving on, so there are these common large precision difficult functions such as division or softmax that are of high interest in private inference. Currently, they take quite a lot of depth. But I think that now we have a discrete CKKS version and a fixed point CKKS version. We could also have piecewise function evaluations for this kind of difficult functions. Further, we really need theoretical error estimation for this to guarantee correctness when we go back to our exact scheme. And so on and so forth. There are many open questions for this. So I'd like to thank you for your attention.
Do we have any questions for Andrea? Maybe one question as somebody who is not quite expert in this field is, these LUT tables, are these usually application specific? How are they, like, who determines what should be used as a lookup table? And
so it's whatever function you want on integer inputs, you can write it as a lookup table, where you, like, for each point in the input, you specify an output. So this is very good if your function is not continuous, for example, and you cannot use the typical polynomial interpolation methods to approximate a smooth function. So that's why, like, SBox is one such example, which is just, random points.
Okay, thank you. All right, let's thank Andrea again. Our next talk will tell us about homomorphic encryption for large integers from nested residue number systems.
Hello, my name is Jaeyoung Kim, and this is a joint work with my amazing advisor, Dan, and I will start my talk right away. So this is a two-line summary of our talk. So we foresee that in some applications of FHE or fully homomorphic encryption, we need to compute over a large modulus, especially predetermined one. And these existing FHE are not so good at such a large modulus. So we design a dedicated FHE scheme by introducing a nested CRT system inside a single ring alpha V ciphertext. So as you all probably know, fully homomorphic encryption allows you to compute in an encrypted state. So given data in the client side, it can be encrypted and sent into the server, and you can compute whatever function and send it back to the client, and the client gets the desired result. The main example or application we consider in our paper is what we call homomorphic signing. And in the following two cases, we need such a large modulus. The first one is universal thresholdizer, where you can compile any signature via threshold FHE to a one-round threshold signature scheme. And the other one is universal binder, where you can compile any signature using verifiable FHE to a one-round blind signature. And when you try to thresholdize or blind well-known signatures like ECDSA or Schnorr, where you don't know how to do like one-round version, you need arithmetic over a large elliptic curve prime, like 256 or 384 beats or more. And existing schemes are not so good at it. So before we talk about like our constructions, like I first want to discuss like if you want to use the existing schemes, which FHE scheme you would choose. So as discussed in the previous talk, like there are mainly 3 different families of FHE these days, the known as like BGB BFP family, CGGIDN family, and like CKKS. And the main difference is whether they support SIMD and their plain text spaces. As you can see in the table, like the very natural choice of supporting large modulus, integer computation, is to choose BGB BFP and choose plain text modulus P to be very large. But there's a big problem here, which is that the noise growth after every multiplication is actually proportional to the plain text modulus P. So like as you increase P to be, let's say, like 256 or 384 beats, then the noise growth soon becomes too large and parameters becomes like nearly impractical. And one side note is that instead one may consider using like the recent development of generalization of PFP. But the main problem of these schemes are that like they only support cyclotomic moduli and not arbitrary moduli, and we consider like modular reducing by arbitrary moduli. Instead of using BGB BFP, we use the discrete CKKS, which was presented like in the earlier talk as a building block. And to briefly describe like or recall what is discrete CKKS, the main difference between CKKS and discrete CKKS is the noise separation. So let me discuss the noise separation of BFP CKKS and discrete CKKS for explanation. So as you know, BFP puts message in the most significant beats and error in the least significant beats. So they are naturally separated. But in CKKS, both of them leaves in the least significant beats. So it's kind of like error always contaminates the message, but it is kind of okay in CKKS because we can preserve some amount of most significant beats of the message. And discrete CKKS works as kind of a hybrid between the two in the sense that we put message slightly higher so that we can separate message and error like in BFP, but also it supports some CKKS multiplications. And in particular, the like recent discrete CKKS framework supports the following homomorphic operations. So the first type is arithmetic operations, where you can compute like addition and multiplication over Z. And second type is lookup table or functional bootstrapping. You can compute any function from ZT to ZT for a small integer t. And the third type is modular reduction, where you can take modular reduced by like any small integer t. And now I want to describe our construction. So we use the whole discrete CKKS framework as a black box. So the rest of the talk will be like more like a fun math talk that you can like build upon a certain homomorphic computer with certain properties. So our baseline is a homomorphic computer which can only support addition, multiplication, modular reduction over Z and R. And the computer is equipped with SIMD or single instruction multiple data for large vector dimension n. So you can imagine a long vector with like dimension like 2 to the 15. And these operations work element-wise. So like in this example, like the first slot is multiplied by the first slot, second slot with second slot, and so on. And the biggest constraint of this computer is that it only supports up to small integers. And because of this reason, you cannot put the entire like 256 into one slot, but like eventually the individual slots will collaborate to represent large integer and like support arithmetic over it. So the first step of our work is what we call asymmetric modular reduction. So in the previous like CKKS modular reduction work, they evaluate a polynomial interpolation to modular reduce. And instead of evaluating all the same polynomial across the slots, you can evaluate different interpolation polynomials, which leads to different modular reduction across the slots. And for instance, you can modular reduce by 7 for the first slot, like 5 for the second slot, 3 for the third slot, and so on. And by using this like a new tool, we can leverage CRT or Chinese remainder theorem to store a large integer within a single ring of W ciphertext. And this is a key idea of how we store large integers. And to talk about a little bit more, so we first assign like k different moduli, co-prime moduli, to generate a CRT system. And when we repeat it again and again to like also provide a SIMD structure. So a ciphertext with vector dimension n can store n over k integers of modulus p, which is a product of pi's. And for the checklist until this point, we have a homomorphic ZP computer for smooth modulus p, which is a product of pi's. And we have a homomorphic ZPI computer for individual I if needed. So the second step of our construction is homomorphic base conversion. And the goal of this step is to support a modular reduction by an arbitrary integer r, which can possibly be much larger than the individual pi's. To solve this problem, we rely on the standard fast base conversion technique in the like a common RNS residue number system world called HPS19. And recall that HPS19 converts an integer x represented under CRT moduli pi into a modular R representation as follows. So the input is like x mod pi's and the output is x mod R. And to understand this formula, the first part of the formula, yi times pi hat mod R, is just a CRT reconstruction. And the second part, minus v times p mod R, is kind of approximating the first part and subtracting from it to get an approximate modular reduction of the original data. And the final modulo R takes modular reduction again, like by subtracting several times. And the problem in our homomorphic case is that the very last modulo R operation is not like so easy. So instead, we compute, we don't compute the very last modulo R and allow some laziness, which means that we compute x mod R plus RE for some small e instead of exact x mod R. But this is okay because like we can still simulate a mod R operation. And to compute this, we cannot compute this directly as a big integer, so we need to compute it with respect to the individual CRT moduli pi. And it can be written as the formula below. And to understand, again, this formula, the blue parts can be solely written as arithmetic over modulo pi. So this is just automatic. We already have a ZPI computer, so this is great. And the more harder part is the red part, v. We called that it was like summation of yi over pi and taking round. And for computing the yi over pi, we need computation for like different moduli, but we can use our baseline real number computer to compute this. And then we need to take round, and it looks hard at first, but the interesting observation is that the rounding is free due to the nature of discrete CKKS. What it means is that we can just first compute the value without rounding, and we pretend that we like computed the rounding. And like the difference or the error can be just included in the noise part. So yeah, this is kind of okay. So the checklist until this point, we have a homomorphic ZR computer because we allowed modulo ZR operations, but we kind of simulate this inside our ZP computer. So we need to ensure that there is no overflow, and we need a requirement that R is less than square root of P. So this already seems to like solve the problem because we have a like modulo R computer for arbitrary modulus R, but like there is a problem which is not enough small primes. So what it means is that the CRT moduli PI needs to be co-primed to each other, but there are like only limited number of primes less than a certain bound. So for instance, there are 31 primes less than 128, which can be represent at most the product of all prime powers less than or equal to 128, and it is less than like 117 beats, which is not sufficient for our application. So to solve this problem, we introduced an extra CRT layer upon our CRT. And similarly, as in our first step, we can use different R across our ZP slots. So we can use, let's say, R0 to RL-1, like for the next CRT system. And then we will have N over KL many ZR slots with a smooth modulus R, which is a product of Ri's. And again, our next checklist is that we have a homomorphic ZR computer and a homomorphic ZRI computer if needed. And our very last step is to simulate or repeat what we did in step 2 in our second layer. And so we need homomorphic base conversion, and recall there that we needed 3 different operations, which are like arithmetic, real number, and rounding. So arithmetic is like automatic because we already have ZRI computer. But the problem is that like real number arithmetic and rounding are no longer available because now we don't have our baseline real number computer, right? So to solve this problem, we kind of simulate a new CKKS inside this new RNS system and solve this problem. For time constraints, refer to our paper for more details. In the final checklist, we have a homomorphic ZS computer for S less than square root of R, where recall that R was a product of Ri's. So for the summary, we have like a very first CRT layer, and we have homomorphic base conversion to construct the next CRT layer. And then finally, we have a homomorphic computer that supports like ZS arithmetic for arbitrarily large S. And we observed that the size of S or logarithm of S can be at most like proportional to the vector dimension n, which means that we can support up to like 2 to the n like size modulus. It's like 10,000 or 20,000 beats, so it is quite sufficient for our applications and also significantly better than the existing solutions. And we check our idea with experiments. So for smooth modular multiplication, which is step 3, we support like 8,000 beats of modulus in like 18.4 seconds in latency and 4.6 seconds in throughput. And for arbitrary modular multiplication, we support up to like 2048 beat modulus multiplication with like 47.5 seconds in amortized time. To compare with the existing works, we mainly compare with the well-known TF-HERS in the CGG-IDM world. And for like a 256-bit integer computation, our latency is already like 20 times faster, and like throughput is like 3 orders of magnitude better. So the takeaway is that instead of supporting a large modulus directly, we show how to build like large integer computer from small integer computers like via CRT. And one of the main philosophy of our work is that like sacrificing the number of slots gives you better latency or better precision. And this seems to be happening in the rest of the FHE world. For instance, one may ask, like, is there an analog of this in BGB BFB world? And we think that the generalized BFB, the recent ones, are kind of an analog and for cyclotomic rings. And for a follow-up question, you can ask, like, can we do better for power of 2 or power of radix? And I recently had a work answering this question as positive using partial DFT encoding. This is all of my talk, and thank you so much for listening.
I don't know whether this would work, but have you considered, instead of using multiple primes, using a single prime in a p-adic representation and using the Hensel lemma, which would make your many small primes problem go away?
Oh, you mean like prime powers?
Effectively, yeah.
So we are already using prime powers actually, but the key constraints is like the size of the modules we can handle per modular reduction is kind of limited. So this is really depends on the underlying discrete CKKS framework. I mean the functional bootstrapping one, and the size of the modulus is the biggest issue. So like.
We should talk later.
Oh
I
yeah,
have
maybe we
these
can talk
alumni might solve
offline.
that
Yeah,
problem.
yeah. Okay, thank you.
I have a further question. And what's your advantages of your approach? I mean that you divide large integers into RS component and place it into the adjacent slots in within a single ciphertext instead of placing them into the different ciphertexts.
Oh, you mean what is the advantage between so what is the advantage of putting inside a single ciphertext, right?
Yeah.
So the main advantage is latency, and it was kind of crucial in our case, I would say. I mean, for instance, you can consider like a different different modulus BFB or BGB ciphertext, like and you can concatenate them all, but like it will give a very high latency. It would be like almost, I would say, a very large latency. It's almost impractical. So like we kind of wanted to make sure that everything is happening within a single ciphertext. That would lead to very fast bootstrapping.
But you tag the same message into the one ciphertext, one ciphertext you can compute the less integers.
What do you mean by less?
We will talk later.
Maybe
Yeah,
you can take it offline. Any other questions? All right, let's thank the speaker again.
Thank you.
All right, our last talk will be a virtual one, and it will be on fully homomorphic encryption with chosen ciphertext security from LWE.
All right, so hello everyone, I'm Rupen Yang, and today I'm going to talk about how to construct a fully homomorphic encryption scheme with chosen ciphertext security purely from the LWE assumption. This is a joint work with Zuo Xiaoyu and Willy Susilo. So FT scheme is a special PKE scheme that allows one to perform some computation over a ciphertext without first decrypting it. We will require the basic IDCP security for FT schemes. That is, the three will choose two messages, M0 and M1, and one of them will be encrypted by the challenger. And those three needs to tell which one is encrypted after seeing the challenger ciphertext. The FT scheme allows one to perform any computation over an encrypted data. That means the one who does the computation doesn't know any information about the data. On the other hand, the data owner only needs to encrypt her data and decrypt the computation result, and she doesn't have to perform the heavy computation. This can protect the user data in many real-world applications, such as cloud computing and AI querying services, and can be used to construct secure two-party computations. However, in these applications, the one who does the computation may ask the user to share the decrypted computation result. This requirement is very reasonable in the two PC setting. Even for the cloud computing scenario or the AI querying scenario, even if the server doesn't have the right to know the result, they may try to learn some information by performing some attacks. For example, they may introduce some errors related to the message in the computation result and learn some information about the message while observing if the user will recompute or recur again. Also, it's unclear how much information will be leaked. We should defend against such attacks. In traditional PKE schemes, we also have such concerns, and the standard security notions for PKE scheme is the so-called IND-CC2 security. That is, the three could query a decryption oracle both before and after seeing the challenge ciphertext. Here, the three will submit a ciphertext and learns its decryption by querying the decryption oracle. Also, to avoid the trivial attack or simply submitting the Chinese ciphertext to the decryption oracle. The dossier is not allowed to query the Chinese ciphertext in the post-change query. However, the IDCC2 security can't be achieved for the FT schemes. The reason is that the dossier could perform some invertible computation of the Chinese ciphertext, such as adding the change message by 1. After the evaluation, the ciphertext will be changed and it can be submitted to the decryption oracle. Then after receiving the decryption result, it can know which message encrypted by marks the decryption result by 1. Okay, so in the literature, they also present a weaker CC1 security. This is because the problem happens at the second phase. And maybe we can solve it by forbidding the dossier from querying the decryption oracle after seeing the Chinese ciphertext. And there are a few works that have constructed FT schemes with IDCC1 security. However, security of these schemes must rely on either the random oracle heuristic or some knowledge assumptions. Both are very non-standard assumptions. Okay, so now we have some FT scheme with CC1 security, and based on this, a recent work by MN24 presents the VCC security. It brings back the post-change queries, but requires that all the queries in the second phase must be independent of the Chinese ciphertext. How they can check this? They assume that there exists an extractor that can extract all the details of how the dossier generates the query ciphertext and checks if the Chinese ciphertext are used. And in the construction, the extractor is played by the extractor of the leaky snap. Okay, so now we'll give a very quick summary of the state of the art. So we can say for FT schemes, if we just need the basic IDCP security, then we already know a lot of constructions, and they are from either the standard RW assumption or the circular RW assumption, depending on whether you need a leveled or unleveled FT scheme. And both assumptions are now regarded as standard assumptions. On the other hand, if you hope to get CC security, the standard IDCC2 security is not achievable here. And in the intermediate area, we have IDCC1 security and the VCC security. But both security needs non-standard assumptions. This raises the following very natural questions. How to construct FT schemes with CC1 security, or even more, from the RW assumption or the circular RW assumption in the standard model. And in this work, we show that it is possible to construct a FT scheme with CC1 security from circular RW assumptions. The assumptions we use is exactly the ones used for constructing IDCP secure FT schemes. Based on this, we also define a new security called input verifiable CC security or RVCC security for short. And the RVCC security is structurally stronger than the CC1 security, but it's weaker than the VCC security. Then we also construct FT scheme with RVCC security from circular RW assumptions. Okay, so now we first explain how to construct the FT scheme with CC1 security from circular RWE. So similar to most previous works in this area, we also follow the well-known knowing paradigm. And the construction will involve two instances of the underlying IDCP secure FT schemes. And the message will be encrypted by both of them. The final ciphertext will include both ciphertext components and a proof showing that the two ciphertext components encrypt the state message. The construction is CC secure because in its secure proof, the challenger only needs one secret key to answer our queries, and it can switch between the two secret keys due to the ZK proof guaranteeing that the two components in the query ciphertext must encrypt the same message, and it doesn't matter which component is decrypted. And then we can claim security of each component of the channel ciphertext one by one, and the proof attached in the channel ciphertext also leak no information because it is zero knowledge. Okay, so that is the basic idea why this construction is secure for PK schemes. But for FT schemes, we also need to consider the evaluated ciphertext. And an issue is that how we can generate the proof for an evaluated ciphertext. The proof needs to show that the two components of the evaluated ciphertext also include the same message. One may hope to use the direct generation as in the encryption scheme, but this needs the randomness the encryption randomness of the ciphertext, but that is usually not accessible for the evaluators. Another way is to show that the ciphertext is generated from valid ciphertext honestly. That is, if you see the C1 prime and C2 prime generated here, you can show that C1 prime is generated from C1 and C2 prime is generated from C2 using the same circuit. And C1 and C2 include the same vector of messages. Then, because they are related from the same message, same inputs with the same circuit, then it can show that the C1 prime and C2 prime include the same message. However, if we use a normal analytic proof to prove this, the proof size will be a polynomial in the circuit size here, because in our proof, the statement size depends on the circuit size. And we can solve this problem by using a snark to generate a proof. Here, the snark can generate proof size, can generate very short proofs for very large statement because its proof size is independent of the statement size and the witness size. But if we use general leaky snarks, it needs us to use random walk heuristic or non-forcible assumptions, which are non-standard assumptions. Okay, so that is, if we hope to use the non-union paradigm, it looks like we must use snarks. And it looks like that we must use non-standard assumptions. But here, we know that the restriction of non-standard assumptions only appears if we need a general snark, a general snark. If we only need some special snarks, there's hope that we may construct it from standard assumptions. And in the literature, there are some snarks for some special languages, such as indexed batch NP, language P, or some monotone policy batch NP. There are construction of them from standard assumptions like LWE. But the problem is that these languages are not expressive enough for our purpose. And we will solve this problem in this work by trying to giving construction of snarks for the validity of every ciphertext directly. And our construction relies on snarks for index batch NP or index bug for short. It proves that the circular C can be satisfied for indexes from 1 to n. That is, we can find witnesses W1 to Wn, such as CL1 W1, CL2 W2 until CLn Wn, all output 1. The proof size depends only logarithm of the number n of statements and is linear in the size of circular C. So that is, if we have a lot of statements of the same size or same form with indexes, and each statement is small, then we can get a succinct proof showing that all of them are correct. Okay, so now we have an index bug, and we will try to show that the ciphertext, the validated ciphertext is correct. Our strategy is also to show that the two components of the final ciphertext are evaluated from valid ciphertext with the same circuit. However, we can't prove this as a whole because statement size will be very huge. And inspired by the construction of snark 4P from index bug given in CGD 21, we will prove the validity of each intermediate ciphertext gate by gate. That is, we will divide the whole circuit into gates and wires and commit the ciphertext for the values on all wires using a Merkle tree here. Then we prove that each wire is constructed. Each wire is correct by showing that if the wire is an input wire, then it has a valid analytic proof. Here, a standard analytic proof is sufficient. And if the wire is an internal wire or the output wire, we prove that ciphertext is evaluated from two previous ciphertexts with the same gate. And for all wires, we also need to prove that they are committed in the commitment by the Merkle tree. It's easy to see we can describe this statement by a circuit with indexes, and we can prove them using index bug and achieve the successful proof. And besides that, the proof guarantees that ciphertexts are valid one by one. For the input ciphertext, this is guaranteed by the additional executive proof. And for the other ciphertext, this is because all previous ciphertexts are already proved to be valid. And now we get this new ciphertext from them via the correct computation, and it must also be valid. Looks like that we have done everything. This can serve as a proof system for the validity ciphertext. But the bubble construction and proof works only if the underlying index block has a global soundness. That is, the proof can guarantee that all the statements it has proved are all correct. However, for all known index block from standard assumptions like WE, they only have local soundness. That is, it only guarantees that one single statement is correct. That means we only have one chance to check the validity of statements in the final secure proof of our FHE scheme, and we must know which statement to check in advance. So to solve this problem, we will modify the Merkle tree we use for commitment and let it to report which statement might be wrong. Here we give the Merkle tree the secret keys of the two FHE schemes and let the tree to report the if node with invalid ciphertext. That is, the tree will decrypt the two components of the ciphertext and check if they are the same or not, and report if they are not the same. As the check needs the secret keys, which should be kept secret, we will increase them using another FHE scheme, and all the checks are done homomorphically. Then in some steps of our final secure proof, we will give the challenger the secret key of the third FHE scheme as a trapdoor, and it can use it to know which ciphertext in the tree is invalid. The solution here is not complete yet. This is because an invalid ciphertext may be due to a wrong evaluation or an invalid ciphertext in its inputs. So maybe the statement here is correct, but a previous statement may be wrong. However, we can't include all the positions because we need to keep the commitment succinct. To solve the problem, we will check the wrong statement layer by layer. The logic is that if we have an invalid ciphertext, either the current statement is wrong or there must be some invalid ciphertext in the lower layer. For some reason, we are not able to explain the details, and please refer to our paper for more details. The construction is inspired by the predict extractable hash given in BBK plus 23, and we extend their primitive to present a new primitive called predict extractable commitment. Okay, so now with our new snark for the validity of the ciphertext, we can prove the system-wide security of the construction with the standard knowing paradigm. Next, we will briefly explain how to achieve the strong security of RVCC security. So our RVCC security will weaken the VCC security given in MN24. In that definition, they will use an extractor to extract all the ciphertext used for generating the queried ciphertext. And in our definition, we will let the dossier to submit all these input ciphertext for the queried ciphertext, and we don't have to use the very strong extractor. And the challenger will check if the challenger ciphertext appears there. Of course, we can't trust the dossier, and we need to additional verification algorithm to check if ciphertexts are correct or not. And to enable this, we add a third Merkle tree in the ciphertext, which commits all the input ciphertext used in the evaluation, and use the index block to prove that all the input ciphertexts are correct. Then, the verification will try to rebuild this Merkle tree and compress it with the one in the query ciphertext. This could guarantee the correctness of the submitted input ciphertext set. Okay, so now to conclude, in this work, we push the boundary of security for FHE schemes that can be constructed from standard assumptions, from basic IDCP security to the CCY security, and then to the RVCC security. To achieve this goal, we construct a special arc for the validity of FHE subtext using index block and a new tool called predict extractable commitment. Okay, that's all for my presentation. Thanks for your attention, and I'm happy to take any questions online. Thank you.
Unfortunately, we cannot take questions for the virtual speakers. You will have to reach out directly to the authors. But let's thank everyone who spoke in this session before we adjourn for a coffee break.